So now we've seen the basic data structure that we maintain, including the mutex relations. We've seen how forward planning graph expansion works, and we've seen how backward search in the planning graph works, which means we can now put all this together and finally come up with the Graphplan algorithm. And here is the function Graphplan that takes a propositional planning problem consisting of a set of actions, an initial state, and a goal description. And the high-level structure of this algorithm is as follows. We first expand the planning graph until we get to a graph that may contain a solution. And that's what happens here in this part. And then we try to extract the solution, which happens here and again in this loop, and see if this fails. We've got to expand the planning graph again. So this loop continues to expand the planning graph, now also doing the backward search in the planning graph. And now in more detail. So we start by initializing some variables. I is the layer we are currently looking at, that we're searching at. Then we have the no-good table, we have our proposition layer P0, which is initially the initial state, and we have our planning graph, which initially only contains the proposition layer P0. Then in this loop, we increase our layer and we simply expand the planning graph to include the next action and proposition layer, as we've seen earlier in the definition of the function expand. And we have to continue expanding the planning graph until all the propositions in the goal are contained in our proposition layer, in the last proposition layer, and none of them are mutex. That's what these two conditions are. But we also need to stop this loop when we've reached a fixed point in our graph. Then this loop is followed by this if statement here, which simply tests the reason why we have stopped our algorithm. If we stopped because we found a proposition layer that contains all our goals and none of them are mutually exclusive, then we can continue. Otherwise, we have to return failure. That means we basically stopped our loop because we found a fixed point, but not our goal yet. So now we have a planning graph that may contain a solution plan. And the first thing we do is we remember the size of the no-good table here. And the reason why we do this is because this tells us when we have to terminate in our algorithm, as we will see shortly. So now we have reached the point where we can try to extract a plan from our planning graph. And we do this here, store this in our variable big pi. And if this was failure, so we can't find the plan in this planning graph, then of course one option is to expand the planning graph with another set of layers. And then again we try to extract a plan from this planning graph that now contains an additional action and proposition layer. And again we store this in our variable big pi. Now, if the returned value is an actual plan, that means we have won. We can return this plan as a solution. So we test this in the next step. We test whether this plan was failure. And if it's not, then we go to this loop. If it's still not failure, then we come to the point where we return our solution plan. But if it was failure and we have reached a fixed point in the plan, so an expansion of the plan will no longer give us more propositions or more actions in our action layers, then we have to test whether we need to terminate. And our condition for termination is now this. If the size of the no-good table did not increase, so we still found exactly the same nodes and failed at exactly the same nodes, then an expansion of the graph will not do us any good. And that means we can return failure. Otherwise, we store the size of the no-good table and remember that for the next iteration of the loop. So that was the detailed Graphplan algorithm. And here are a few final words about properties of the Graphplan algorithm. And in short, these properties are that the Graphplan algorithm is sound, complete, and always terminates. So this means that the Graphplan algorithm returns failure if and only if the given planning problem has no solution. Otherwise, it will return a layered plan, the structure we've described before, that is a solution to the given planning problem. And this plan will consist of a minimal number of layers. But that does not mean it will consist of a minimal number of actions, of course. So in that sense, it's not guaranteed to be optimal. But we have seen that Graphplan works on the propositional strips representation. But again, remember, The strips representation can always be translated into the propositional representation, so that is not really a restriction. The important thing here is that Graphplan, when it came out, was really a lot faster than all the previous planning algorithms we've described so far. So it was really a step forward in performance. And a lot of that has to do with the basic data structure it maintains, the planning graph. The backward search itself is, of course, rather inefficient and still requires exponential time. But it is the reachability analysis that is performed by the planning graph that gives the algorithm a lot of power. So that was the Graphplan algorithm. Graphplan solves the same planning problem as state space search or plan space search. But it does so in a very different way, namely by first generating the planning graph, the basic data structure that underlies its search. And we have seen here the algorithm that can be used to generate the planning graph, which is forward planning graph expansion. And most importantly, this can be done in polynomial time and tells us something about reachability of nodes. And this forward expansion, together with the backward search, make up the planning graph algorithm.